mathematics. Very nice. So thank you for coming.
Thanks, Bernardo. Yeah, thanks a lot for having me here. It's been a pleasure. Thank you all for being here. I know it's a little late in the conference, so I appreciate having an audience. Yeah, so at heart, I'm a little bit of an outsider here. I consider myself a low-dimensional topologist, and for the most part, I'm most interested in concrete computational questions in low-dimensional topology and the complexity theory of problems in low-dimensional topology. So to that end, in my PhD studies, I actually had to study some obstructions to branch covers of surfaces extending the three manifolds. And so I kind of had this machinery, and in fact, it's machinery I learned from some preprint of Craig Westerland and his collaborators. So it was great to meet him. I had not met him before. Unfortunately, he can't be here right now, but yeah, so I had learned about some problem I'm going to state here momentarily from Carlos Segovia, who's also not here, but he had learned of that problem from this dude, and he was motivated by this evenness conjecture. So evenness conjecture is not true in general. That's what I found. So let me give some setup. So yeah, so probably 2/3 of this talk will be like stuff in the paper with Bernardo and company. This is Andres Angel, and the last third, maybe last 10 minutes, will be stuff with Marco Boggi and Carlos. That's work in progress that we hope to have soon. So great. So throughout, G is going to be a finite group. And I'm always going to think about oriented actions. So I'll have a oriented surface that I'll call T. So I say T instead of S because morally, I'm much more comfortable downstairs in the quotient. Everything I had studied in the past was about bundles as opposed to actions. And there's not a whole lot of difference, but I view a bundle as a more combinatorial type of thing than an action. Okay, because a bundle, you just have a map from pi1 to G. Yeah, so we have this oriented surface, and then also throughout N will be a three manifold. Again, it's oriented with its boundary equal to T. And we're gonna study actions on T. Okay. So the first question I want to address, this is basically a question motivated by Bernardo's evenness conjecture. It says, suppose our action of G is free on T. Okay. So when does it extend? To an action possibly not free. I'm not going to write free here because it might not be free. To an action on N in the way that extends a given action on the boundary there. Okay. So what I'll say here is I'll call this extendable. An extendable action. And you don't have to have this freeness assumption. It just turns out like that. It's like a good test case to study. Having this freeness assumption, you don't have to worry about stabilizers of points on T, and it just makes the analysis a lot easier. And in a way that you can go back later and fill in what happens when you do have stabilizers. So that's the first question. We'll spend most of the talk addressing this. And then the second question, the last third, which is kind of the work with Marco and Carlos, will be about, well, suppose this is extendable and free, maybe not, whatever. So suppose this is extendable. What can we say about N? And I'll come back later and refine, give some more precise things about this question. Say about N. So, of course, the answer to question one is obvious. So this thing is free. This action extends if and only if its class is 0 in equivariant bordism. Right? But that's not particularly helpful. We want to give a more concrete answer. So in other words, you might think of what we're trying to do with question one is compute the piece of the equivariant bordism group that comes from the free actions. And later we're actually able to take what we learned from that and compute the whole thing. That's really the main theorem of this paper. So I will state that in passing, but I really want to focus on the geometry, draw pictures. We're coming back from lunch. It's the end of 4 days. Let's just see lots of pretty pictures. That's the real question. Yeah, question. Yeah.
Why is it important to keep in mind the orientation?
It's not. You could ask these questions for the non-oriented case, and they're great questions, and I don't know the answers. I think Carlos is working on that now. You could ask about other, you could have unoriented, and one answer is that, well, when things aren't oriented, there's kind of obvious obstructions to extendability, and those things poison the computations because they're like you have to deal with them all the time. So here it's easier, in fact, to have an oriented one. So in fact, Bernardo was interested in the case of having a stable unitary structure. And it just happens that in the two-dimensional case, he's interested in all dimensions, stable unitary, equivariant bordism with stable unitary structure. And he wants to know the ring structure, or module structure, I guess. So, but I don't know much about high-dimensional stuff. I'm a lowbrow guy. So, yeah. Any other questions? So these are just everyone on board with what we're trying to do, and I'll be more precise later with what my answers are, and maybe that'll make it clearer what I had in mind with respect to computing too big. So before we really dive in, I'm going to list a few motivations, and so my motivation, like kind of where I was coming from when the things I learned that I realized I could address these questions with. This will be a little bit of a pitch. I'll just say like one thing about it. So fix a group G, say it's a finite simple. So if K is a knot, then you get an invariant that takes K and sends it to the number maps from I1 of its complement to G. Okay. So this is an invariant of knots. Okay. So in the special case, well, it's not a finite simple group, but if G is a dihedral group of order 6, then all right, we would typically also fix a conjugacy class and only count the maps that send a meridian into that conjugacy class. If G is the dihedral group of order 6 and you have the conjugacy class of reflections, this number is exactly the number of Fox 3 colorings. Okay, so these are interesting invariants for distinguishing knots. Okay, but in the case of a finite simple group, we proved is that this is like a subject of my dissertation with my advisor, Ray Cooperberg, and I guess S comes before K today. So this is that this function. This invariant, so in my world, I think of K as a knot diagram, because which is a combinatorial thing I can feed to a computer. And the size of the diagram is the number of crossings in the diagram, which is roughly just how big the picture is. And you want to compute this number as efficiently as possible in the size of the diagram. But what we proved is that there isn't really an efficient way to do that unless P equals NP. So what we showed is that this invariant is sharp P, well, is NP hard. Okay. And why? Well, it's a long story, but it came down to analyzing the Hurwitz action in the Brave group on G. Like if you have tuples of elements in G, you have the Hurwitz action in the Brave group on those tuples, which Craig talked a little bit about. And basically, when the group is finite simple, we studied the crap out of that action. We have a lot to say about it. It's a really interesting and rich action, rich enough that you get this. Okay. So that's my motivation. That's just a little bit of a pitch. But maybe Bernardo's motivation is his evenness conjecture. Well, okay, so Bernardo or whose conjecture is it?
Was there?
Okay, all right. So well, I won't call it your conjecture, but it was your motivation. So evenness conjecture. So I'll explain this in a second. So there's a bunch of results with Landweber. I'm going to forget a bunch of names. Tomazania, like Bernardo and his collaborators. So I'm going to forget a bunch of names, but it basically says that often, if we look at the stable unitary equivariant bordism ring, then group, then this is a free module over the non-equivariant ring. Okay. With generators in even degree. To be frank, I don't really know this story very well. Okay. So the question was, is this always true? So is this true for all finite groups G? All finite groups G? Okay, and the answer is no. That's what I found. Okay, and the reason why is, as Bernardo understood, is that so if this is true, so if you have that this is a free module, so the star here is true, then in particular, well, you can't have well, the answer to question 1 must always be yes. And I learned about this question from a paper of Carlos with an undergraduate, a student of his, where they showed that the answer to question 1 is always yes if the group G is something like a dihedral group or an abelian group or a symmetric group. So that's a lot of different types of groups. Symmetric groups are pretty big, dihedral and abelian are pretty small, but you might think, well, okay, like maybe there's some hope that this is true. But what I realized is the kind of obstruction theory I needed to develop for here can be used to find counterexamples. So I'm going to say more about that in a bit. And before I do, let me get one more motivation. Got that all the way up there. I tried. Okay. Maybe I didn't even want to do that. Well, anyway, never used one of these boards here. There's a whole S3 here I have to grapple with. It's complicated. So the answer to question 1 was not known. Yeah. So well. In all cases, it was no. In all known cases, every free action extended, and what I found were examples where they don't. Yeah. So, and now this one's gonna be somewhat out of left field. So I gave one motivation. There's another motivation. This is really a motivation I learned from Marco, which is the Putman-Weiland conjecture. And I'm not going to be able to solve this conjecture. So this is really something coming from geometric group theory, or the group theory of surfaces. And what it says, the conjecture is the following. It's that if T is a branch cover of S, then, well, okay, let me pick a class in the homology of T. Just with integer coefficients. What happens is, well, the mapping class group of S, there's a finite index subgroup of mapping classes that lift to give you mapping classes on T. Okay. And the conjecture is that so that subgroup, I'll denote mapping class group of S that somehow plays nice with T. They're the liftable mapping classes to T. The orbit of this gamma under this mapping class group is infinite. Very simple little statement here, but it's eluded them for a long time. I haven't spent much time thinking about this problem, but I'm going to return to this later. So yeah, I think that's all I'll say about this for now. So much for motivations. Let me do a few preliminaries.
Can I point you for a second?
Yes.
How does the Ibn's conjecture imply that question 1 is true?
Yeah, so well, basically, because if question 1 is false, you have Gaussian tests. So I'll defer you to him for that. You can ask him more later. Yeah. So, as I said, I'm the low dimension guy. So any other questions? Whether or not I can answer them is another. Okay, so preliminaries here. So something I already said is that free G actions on a surface are the same thing as bundles on the quotient. With whatever, appropriate notion of equivalence. So S for me will be the quotient of T by G. And so if I quotient a free action, what I get is a surface that naturally has a bundle. Okay. So, and maybe a point, so that's maybe first preliminary. And another point is it's kind of a miracle, really. So it says that if this extends to n, then in fact, n mod g, a priori, there's no reason it has to be a manifold, but it is. Okay, so it's always some orbifold thing. But what I mean here is n mod g, just as a naive quotient, it is a manifold. It's a three-dimensional manifold. Okay, but of course, M really has extra data on it. So so really, we should think of M as an orbifold. And you might think of it as like a global good orbifold. So what's really going on here? Well, the reason why is that, let me remind you, what are the finite subgroups of SO3 of conjugation? Right, so where can something go bad, right? If n mod g is not a manifold, it goes bad where there's somewhere when there's a point with a non-trivial stabilizer, right? But that non-trivial stabilizer has to be a finite subgroup of SO3 because we're looking at orientation preserving actions in dimension 3. And these things are pretty simple. They're either cyclic, dihedral, which I'll denote as D2n, dihedral group of order 2n, or platonic. And there's the three platonic symmetries, A4, S4, and A5. So that's the tetrahedral symmetry group. This is the, what's S4? The cubical or octahedral group, and A5 is the icosahedral. Okay. So, and if you look at any of these actions, the point is, if you look at any of the standard actions of these groups on the 3-ball, the quotient is another 3-ball. Just a naive quotient. Okay. So, but this M, as I mentioned, it's an orbifold, so it really has some extra data on it. And this is where I really have in mind, like making the problem combinatorial, is looking at that extra data. So,
Could you explain why the quotient is again fold? Why?
Oh, it's clear. The cyclic group.
You change something.
Yeah, these are all well,
These are not rotations.
These are only rotation. These are the orientation preserving subgroups. But yeah, I don't know. It's an exercise. Yeah, yeah. So you can convince yourself.
So it is manifold, but there are points where you do have isotopes. So it's a topological manifold.
It's an orbifold that's underlying space is a manifold. Yeah, that's all I'm really saying. But now I'm going to decorate this thing with the orbifold data. Okay, so M has orbifold data along its branch locus. So let me give you some definitions. So the ramification locus gamma tilde of the G action on N is the following. It's just all the points in N whose stabilizer in G is non-trivial. Okay. And the branch locus of this action is the thing is gamma tilde downstairs. So that's gamma tilde. The branch locus is gamma, which is gamma tilde mod G, and that's a subset of M. Okay, so gamma tilde is a subset of n, the thing upstairs. And so a key point, this is maybe the key point. Is that both gamma and gamma tilde are topological graphs embedded inside of their ambient manifold. So I'll draw a picture in a second. So they are topological graphs where the vertices correspond to points whose stabilizer is not cyclic. Its stabilizer is either dihedral or platonic. So the vertices are points with non-cyclic isotropy. So it's either dihedral or platonic. And let me draw a picture. And I guess, Bernardo, the answer to your question, why is it topologically anormal, is, well, I can just build it for you directly in all three cases. 2, 2, 0, 2, 2, n, 2, 3, 3, and 2, 3, 5. Right? So did I say that right? 2, 3, 5? Yeah, 2, 3, 5. So yeah, here's an example. And this isn't a free action, but the point is this is showing you what's going on locally. So so I'm going to have S2. S2 is my T. And G will be D6, the symmetries of a triangle. And I might think of that triangle as sitting here, an equilateral triangle sitting in this equatorial disk. And if you look at the action of D6 on this ball, you get points with isotropies. Of course, the center of this ball right here, its isotropy is all of D6. Okay? All the other points to isotropies are cyclic subgroups of D6. And those cyclic subgroups will correspond to like invariant lines under the action, right? So I get all those, yep. And then there's one more kind of sticking up this way. Okay, so I'm kind of cutting up this ball into like fundamental domains, if you will. Well, almost. But so that's T. B3 here is my N. So this ball in here is N. And if I quotient this whole picture by G, what do I get? I get the following.
The fundamental domain is like an orange wedge.
Yeah, something like that. Yeah. So this will be like 3, 2, 2. So, and now the point is the red thing here is gamma, and the red thing here is gamma tilde. So that's the ramification locus, that's the branch locus.
So this claim that they're both graphs, you need G to be at least. Couldn't with the action, couldn't you have a surface of fixed points?
That would have to reverse the orientation. Right, and I'm not allowing that. That's a great, yeah. That's where things get complicated. If you try to do the non-orientation preserving case. Yeah. So somehow mixed up black and red here. Cool. Any other questions about this picture, this example? So right, these platonics, right, these correspond to a picture like this with 2, 2, n. This a cyclic is just an n. And over here, these are whatever they are, 2, 3, 3, 2, 3, 4, and 2, 3, 5, I think. Yeah. So you can just directly construct. That'll answer your question. Okay.
Sorry.
Yes.
I just find this really nice. Do you know a criteria for when you can guarantee that this happens? You have an action of a group on a manifold for the function. is also manifold? You're doing like three
Well, I mean, it's going to get more complicated than higher up you go in dimension, right? So if it's always an orientation preserving action, then there's going to be a similar story here, but you're going to have to understand the finite subgroups of SOD, where D is the dimension. And that just gets, they've been classified, I think, up to SO5. But yeah, people maybe have gone further as well. And things just get really complicated because you can have irreducible, or sorry, you can have reducible subgroups, right? So not so good. Cool. So, all right, these are just the preliminaries. So you should think of like when you take the quotient, you have this manifold M that has some closed topological graph, right? Because the G action on the surface is free, this graph is like a closed up graph. There aren't any vertices terminating on the boundary of them. It's all closed up. I think I want this one. Cool. Yeah, so now let's do a bunch of warm-ups. In some sense, that was a warm-up, but that's kind of giving you a sense of what's going on locally. But do some global warm-ups now. These are going to be important. So first, let's suppose we have an action of G that's free on T such that the quotient S is a torus. Well, if the quotient is a torus, that means T itself is a disjoint union of tori. Okay. This might not be a connected cover. So it's easier just to say, I just want my action to be free in the quotient of torus. Okay. So then the claim here is that the action always extends. And in some sense, it's this example right here that is the most important example for understanding the obstruction theory that we developed. Okay. So why? Well, let me draw S for you. So S is supposed to have a bundle on it. So let me fix a base point. And we have these two monodromies, maybe A and B. And of course, A and B, they commute inside of G. But the point here is I can fill this in. It's not going to be free, but you can glue in a disk here, and you get a ramification locus in the interior. That's a single. It's the core curve of this solid torus. So there's ramification along that whole thing. Okay. So that, yeah, I mean, you can think of this as taking the surface and adding a handle to it, but an equivariant handle, where that handle has a rotation given by the action of A, and I'm gluing that in, and then you glue in another handle in here. So there's a two handle, and then there's a three ball, like a three handle in here to cap it. So any questions about this example, what I'm saying here? The point is that because we get to have ramification when we extend into the interior, well, we can do that. And in fact, this example, I could have done it one dimension lower, right? Any action of a circle, if I have an action of a group on a disjoint union of circles, so that the quotient is a single circle, well, if I insist that the extension be free, that'll happen if and only if the action was a trivial action. But if the action is non-trivial, then there's some monodromy around this circle, and well, you can always fill it in if you're allowed to have a ramification point in the middle, right? And I'm just kind of doing a mapping torus version of that here. So in other words, what I'm saying is that the first equivariant oriented bordism group of G, at least the torsion of it, let me be careful. Well, all right, what am I saying? It's basically true, but let me not write that because I'm going to say something. Okay, so that's the first warm-up. Let's do another warm-up. So now I'll suppose instead of, it's kind of similar in spirit, but I'll suppose G is abelian. Then the claim here is that every action extends. Every free action extends. And let's just suppose, I'm going to take my S it's some surface. I just assume it's connected. So this is S, this is my T mod G. And the point is, if it's abelian, then the monodromies around the separating closed curves on the surface have to be trivial. Why? Because the monodromies in pi1, this loop is a commutator. But if the group's abelian, that has to be trivial. So you can fill these in, and then you're just left with the disjoint union of tori, but we know how to fill those in using that. So the abelian case is also done. Okay. Cool. And now let me give one more warm-up. And this really deserves to be called a lemma. And there's a more general result than what I will sketch due to Rennie and Zimmerman. This is from 97, I think. What they say is that every D2, every dihedral action on a surface extends, okay, which is good for us, but it's actually even nicer. It extends to a handle body. And let me prove this in the case that the action is free. So first of all, I also might as well assume that the T is connected. It's not hard to deal with it when T is not connected. So if I look at S, so I'm going to draw S down here. S is this surface here. S is T mod G, where G is the dihedral group. Well, if the bundle on if T is connected, then that means the bundle on S rejects G, right? So that means. And now G is a dihedral group, and you can never generate the dihedral group with just rotations. You have to have at least one reflection. So I might as well draw that reflection here. Okay. So I have a reflection there. But then we do a similar thing with these separating curves. So the separating curve is a commutator, but commutators in the dihedral group are always rotations. So this is a rotation. And what that means is you can fill this in a consistent way with a 2 to n here. Okay, and then you can keep going. You can extend across. You just pick up Pants decomposition now. You know, once I fix that one, and I get an n there, and then well, there's some case work. Is this curve here a reflection or is it a rotation? If it's a rotation, then you just kind of extend it through like this, and there's nothing over here. The monodromy around that's trivial. So this is like a n case. But if this were a reflection, then that would also have to be a reflection. You'd not get another 2 to n. And you can just keep going. And in fact, it wind up, this also has to be a 2. So this will be a reflection here, and then, well, that'll have to be a rotation. Okay. So it's just basically a direct construction is the point of this. And the direct construction works. It's particularly simple in the free case, but it's really not so hard either in the non-free case. So that's the idea of the proof. I definitely didn't explain it very carefully, but yeah. So cool. So those are most of the warm-ups. And I can more or less, the proof of everything from here out, for the most part, it just comes from combining these things in certain ways. Okay. But before I state theorems, let me introduce some terminology. So let me have a free action G 1T, and I'll say it extends freely if we can find n, you know, an extending manifold that acts free. Okay, and you can think of this as saying that the ramification locus is empty. And now I'll say it extends non-singularly if, well, there exists a three manifold with boundary T, with G acting on that three manifold no longer freely, but what I want is that the ramification locus has no vertices. In other words, what I'm saying is that if a point has isotropy, it can't be dihedral or platonic. You only allow cyclic isotropies. And then the third thing is just I guess the extending, but not singularly. So I would say extends only singularly, only singularly. If it extends, but never non-singular. So you need non-cyclic isotropies. Okay, now let me start stating some results. So the first is a lemma, which I don't think I spelled out as well as I could have, but I essentially knew it in E21. Says that an action, a free action, extends non-singularly if and only if the class of this action, considered as a class in the second homology of G, with Z coefficients, is a sum of toral classes. So what do I mean by that? I just mean classes represented by actions on tori, or disjoint unions of tori. Free actions on disjoint unions of tori. Okay, and the proof is really just a picture. Okay, here's my surface. I'm thinking downstairs. This is the quotient. Okay. There's some bundle on it, okay? And it extends. Here's M. There's stuff in here. It's some three-dimensional blob, right? And now I'm assuming it extends non-singularly. Well, what does that mean? That means the ramification locus, or sorry, the branch locus inside of M, I guess I was drawing in red, it's just some disjoint union of curves, right? Now they may be linked together in some interesting way. Might have a trefoil knot or something. If I can do that. I don't know, it's some linked up stuff, but this is the ramification locus. By assumption, there's no vertices. So it's a link inside of M. And now just take the regular neighborhood of this link. Be a disjoint union of tori. So the boundary of a regular neighborhood of the ramification locus is a disjoint union of tori with G bundle. Right. So, and the point is, this M also has a G bundle that has ramification along the branch locus, but in between the tori and the surface S out here, the bundle is just a bundle. There's no ramification because we hit it all inside the tori. So that gives you one half, and the other half is even easier. So, okay, there's that one. And from there, I was able to get the counterexamples. But the story got a lot more interesting. So let me give you the counterexamples. So the corollary to this is that if the order of G is odd, well, guess what? The dihedral groups always have even order. So do the Platonic symmetries. A4, S4, A5 are all even. So if the order of G is odd, then it can't have these non-cyclic isotropies. Okay. And what that means now is that if G is odd and the toral classes do not generate all of the Schur multiplier, then there exists a free action of G on a surface that does not extend. And I had to work really hard because I had studied this thing, the toral classes inside the homology in my dissertation work, and in particular, what I was interested in was the quotient, right? I wanted to know Schur multiplier mod toral classes, and in my previous work, I had called it the branch Schur multiplier. It's basically something to do with branch covers, but I never actually computed it. I was working with it for 5 years in grad school, but I never computed a single example. And then I realized, well, all right, how do I find one that's non-trivial? And well, all right, I guess I have to actually program for once in my life. So I wrote some functions in GAP, and what I found is that among the odd order groups, the smallest odd order groups that have a non-trivial Schur multiplier mod toral classes have order 243, and they're the following. I'm using Yvonne's notation. The GAP group order 243 with ID 28. But there's actually 3 of them. They're isoclinic. So these are P groups. They're powers of 3. What is it? Is that 3 to the 6 or 3 to the 7? I never remember. 3 to 5? Yeah. Oh, it's 3 to 5? Okay, cool. Well, if you say so. So I don't know. GAP found it for me. So these guys are such groups. Well, here's the issue. This is my story. So I wrote these functions because I'm like, oh, I don't know what this thing's called. So I spent, when I talked to Carlos about this problem, I must have spent a month. This was like in peak pandemic lockdown. I spent a month looking through MathSciNet trying to find this thing, homology mod toral classes, and I could not. So I had to go write it myself. About a week later, after I find the counterexamples, I learned that this thing's homology mod toral classes is called the Bogomolov, and that is implemented in half. So yeah, so I basically had to reinvent that, but it's okay. It was a good practice. Sorry. Yeah, I guess so. Yeah, yeah. Only I were so lucky back. So yeah, so let me say a few things about this part of the story because it's very interesting. I think in some part. This, I don't know, I don't want to put words in Bernardo's mouth, but I think what we found here is in some sense an example of what's going on at the motivation of this conference. Okay, so this Bogomolov multiplier, what is this? So think of the definition. So this is what's that?
This proof that this is the motivation.
Okay, cool. So this thing is called the Bogomolov multiplier, denoted BO of G. And it's really the homological Bogomolov multiplier. Just like the Schur multiplier has different embodiments, right? You can have the cohomological Schur multiplier and the homological Schur multiplier, and they're isomorphic, but not naturally. The same thing here. So and well, what do I want?
Can you please change marker?
Oh yeah, sure. Okay. Yes. So the fact here, going back to Saltman in 84 and Bogomolov in 87, and hence Saltman did some construction using what's called the unramified Brouwer group. I had no idea. Bogomolov understood it, purely group theoretic. Okay. And what we have is that if the Bogomolov of G is non-trivial, then the complex Noether problem for G, it has a negative solution. So let me be a little more down to earth. Right, so Noether was after the inverse Galois problem, and she realized that if you have a group where anytime you have a representation of the group if you have a faithful representation of the group such that the quotient algebraic variety is rational, then you can solve the inverse Galois problem. Apparently, I don't know that, but this is true. And so what this is saying, a little more down to earth, is that the following, if we have a representation of G into some complex vector space, V is complex, then the field of rational functions of G invariant rational functions is not a purely transcendental extension. I said this was more down to earth. I don't know if that's more. Yeah, that's another way to put it. Yeah, so maybe I'll just say that. So it's somewhat more geometric. So I can say V mod G is not rational. So it's not birational to complex projective space. So I mean, I don't really have anything new to add to this observation we made a few years ago, but it's an interesting question. Like, what does bordism have to do with this Noether problem? Is there like a more direct understanding of what the relationship is here, other than that this Bogomolov happens to obstruct in two different problems? Cool. So yeah, let me state a few more theorems. We'll call it a day. Because I've been fussing about these isotropies, but one of the really cool things we found, because Bernardo found, is that you don't have to fuss with the isotropies. So here's the theorem, and this is in our paper, our recent paper. It's not really, I don't know, it's not in there explicitly, but it follows from what's in the paper. So it says that if let G be any group, any finite group, then every free action, so then let me say it again. So then there do not exist actions, free actions, that extend only singularly. So we didn't word things this way, but this is something I thought was really nice. And the proof, so what does it mean to extend only singularly? It means you have the ramification with Platonic isotropy. So the proof is to blow up points. Well, all right, I guess I had a plan, which was to make you answer the question. What do you do? What do you do? You blow up. So you blow up the points. I blew my joke, but so blow up the points with Platonic isotropy. And then apply Renyi-Zimmermann. Or rather, so then you apply a fact, it's actually, I guess it's due to Carlos and his student, Dominguez, Jesus Emilio, who is a grad student at Maryland now, my understanding. The result that says that the Bogomolov of a dihedral is true. So what does this mean? Why is this a proof? Well, if you have a Platonic singularity and you blow up that point, you replace that single point of isotropy with several points with a network of points of isotropy, but that network of points will correspond to invariant lines in the projective representation. Okay, and if you just do the calculation for the three different Platonic symmetries, you see that every line, any line with isotropy, it's always a dihedral at worst, or a cyclic isotropy. And so that that blows up the network, the platonic singularities, you get a much bigger ramification locus now, but at least it's only dihedral. And now, well, you can drill out a neighborhood of that dihedral network that's now a surface with a free dihedral action on it. And because this is 0, you can fill it in without using singularities. So yeah, that was really satisfying. So I think Bernardo got this blow up idea maybe from the algebraic geometer. So
What do you do again?
so okay, where does that leave me? About 5 minutes left. Yeah, so yeah, maybe just to wrap this up, this portion of the talk, and then I basically just gonna have to rush through the stuff with Carlos and Marco. This is really the main theorem, I guess, one way to put it, of our paper. Rather than this, we don't have this actually stated anywhere in it. It says that so we can either work with so if we look at the two-dimensional equivariant bordism groups, and it can either be oriented or stable unitary, whatever, then the torsion of this group is exactly a sum of Bogomolovs. It's you sum over the conjugacy classes of all subgroups, and then you take the Bogomolov of the Weil group of that group. So yeah, so I mean, there's definitely more to this. I won't have time to prove that, but you've seen a lot of the tools that go into it, a lot of the geometric tools that go into it. Okay. So, all right, and now in my last few minutes, let me state two versions of question 2. So, and I think I'm going to skip one of them. So let me state just one more refined version of question 2. So what it says is that what I can ask for is basically, when does the Renyi-Zimmermann lemma hold? Okay. When does a group action? So when does a group action on a free group action on free, maybe not free, they don't need free. When does a group action on a surface extend to a handle? So first of all, it doesn't make sense to ask if the action doesn't extend in the first place, but now we have the whole obstruction theory to know when it doesn't. So if this extends, can it always be made to extend? To a handle body. And I suppose the theorem here and credit where credit's due, it's really Marco's construction. And I won't have time to talk about the construction, so rather let me just assert that this is work in progress with Marco, me, and Carlos. I guess me and Carlos. Is that there exists a G with a free action on a surface that does not extend to any handle body. Okay, so you basically take very roughly, what you do is you start with the surface of genus at least 2, you pass to its you pick 2 primes, P and Q. You pass to its P homology cover, Z mod P homology cover, then you pass to that thing Z mod Q homology cover. And then by some reasons that Marco understands better from old work of his, that this will happen. Okay. So we are writing that up now. Right. So yeah, so it'll be an extension of yeah, what group is it then? It's well, it's some metacyclic group. Or sorry, it's some metabelian group. Yeah. I mean, the deck transformation groups are the homologies, the Z mod P and the Z mod Q homologies of these surfaces, so it's some metabelian. Yeah. Yeah, so basically that the group, the construction works so that the group you have, just by easy calculation, the Bogomolov is trivial. So it always has to extend, but then there's some combinatorial conditions that an action that extends to a handle body must satisfy, and we can hold. Yeah, but I must say, I don't really understand those combinatorial conditions in a satisfactory way, which is why I can't really explain this great in the last couple minutes here. So yeah, let me I think rather than talk about the motivation for this, I mean, so the motivation, I'll say some words. So the motivation comes from this Putman-Weiling conjecture. And what we have is that if the action extends to a handle body, then the cover T over its quotient has this property that the homology of the cover is generated by curves whose image and the quotient are simple closed curves. Okay, and so it's known that the subspace of simple closed curves is always a symplectic subspace of the homology of T. And the fact that it extends to a handle body tells you that it's actually going to have to be, it's going to be a symplectic subspace that contains a Lagrangian subspace. So that means the simple closed curve homology of T, considered as a branch cover over T mod G, has to be everything. And a recent paper of Marco and Andy Putman and Nick Salter shows that whenever the simple closed curve homology of a branch cover is the entire homology, then this Putman-Weiling conjecture holds. Okay. So that's that in a nutshell. I won't write any of that. I can't really do any more justice than what I just said. So let me say one more thing and then I'll be done. So I will talk about one more variation of this question too, which is, am I out of time or not? I guess doesn't matter. Okay, I have 1 minute. So I'll give myself 1 minute. So, and then I'll take 2 minutes. Cool. So here's the question. If I have an action, free, whatever, maybe not, that extends, is it possible to extend it non-singular? So we know it extends non-singularly, right? Right, if it extends, it must extend non-singularly. That's this blow-up construction. And the question now is it possible to make the branch locus? So we can make it the branch locus. Remember, it's a graph embedded inside the quotient of the quotient 3 manifold, and we know we can make that graph not have any vertices, so it's just a disjoint union of circles. It's a link inside the 3 manifold, and the question is, can we make it have just one component? So can we make it a knot? And let me just say some things about this. So here's a lemma. The lemma is that if the Bogomolov of G is 0, and the Schur multiplier of G is cyclic of prime order, then the answer to this question always is yes. Okay. So, and why am I talking about this? Because what I'm interested in are simple groups. Right. So we have, right, I told you about these counterexamples. They were P groups. So they're very far away from being simple groups, interesting simple groups. And the question is, a question I had is like, well, does any action of a simple group, a free action of a simple group on a surface not extend? Okay. But the answer is no. All actions do extend. So, and this is really, I think, a rather fascinating thing about the classification of finite simple groups. So let me note, for most finite simple groups, G, the Schur multiplier, is either 0 or Z mod 2, or Z mod B, for small p. Not all of them, okay? And then there's a theorem of Kunyavsky, I think from 2012, thereabouts, is that if G is finite simple, then its Bogomolov vanishes. So I think there's a very interesting kind of phenomenology of finite simple groups one could tease out of this. Because basically, the Schur multipliers of all finite simple groups are understood. And most of them, it's very close to trivial, or it's either trivial or close to trivial. So I can use this lemma to guarantee this. And at the end of the day, what this is coming down to is, well, for the finite simple, the kind of exceptional in the sense that their Schur multiplier is not small. For those, we would want to understand generators of the Schur multiplier. So the question here is vaguely understand toral generators. Right. So we know the Bogomolov of a finite simple group is trivial. So that means tori generate the Schur multiplier. And we want to understand how few of them do you need, roughly. So, and one can use like representation theory to actually understand these things. And so I guess I'll leave it at that. Thanks for listening.